Welcome. Let me say something about the Lefschetz fixed point theorem in the finite. I proved the theorem in 2012, which is the statement of the classical fixed point theorem of Lefschetz. You can find it, for example, in Griffiths-Harris. And in the continuum it's quite heavy because you have to make assumptions on the map. We can read, for example, we need that the fixed points are isolated and that they are non-degenerate. There is some condition on the Jacobian matrix which has to be satisfied. So what happens in the finite, which is very nice, is that we don't need any assumptions. So we can take any, for example, automorphism of a graph and then look at the induced map on the Whitney complex, or we can look at endomorphism of a graph. We can also look at just the simplicial complex from the very beginning and look at a simplicial map. But more general is even when we look at a continuous map. So I think this is a nice way to think about topology on a finite setting by introducing a classical finite topology, and that's what Alexandrov did very early on. And we can then say what is a continuous map, like, you know, the inverse of an open set is open. That gives us a continuous map. What happens is, can we do the Lefschetz fixed point theorem for arbitrary continuous maps? A tractor of a continuous map doesn't have to be open, doesn't have to be closed. I currently just need the assumption that the tractor, just the omega limit set, the intersection of all the images of the map, is either a closed set or an open set. The reason is because we need cohomology on that attractor, and cohomology is given when we have open sets or if you have closed sets. So the definitions are again here. So we have the set of fixed points, the set of simplices or elements in G which are fixed, and we can define an index for each of these simplices, which involves the dimension and the induced map on the simplex. So there's a sign of the permutation. And then we have also cohomology. We have calculus on a simplicial complex, on an open set or a closed set, and we can do that by just introducing this exterior derivative d, which is a matrix, an n times n matrix if the complex has n elements, and then we have the Hodge Laplacians, and we can look at the Betti numbers. We can look also at the linear space. The linear spaces are the cohomologies, harmonic forms, and when we have a transformation, this induces the Koopman map, which is a unitary on the attractor. If you have invertibility, this is a unitary map, and then we have also the e to the minus th, which is the heat flow. So that makes sense because h has non-negative eigenvalues. So the heat flow is in the limit a projection on the harmonic forms, like what you have in the classical PDE setup. Now, very important is this McKean-Singer symmetry, and so the only thing we really need is this symmetry. And so in order to have this symmetry, the only thing we really need is this Dirac matrix. So this whole setup is very general. It works for any cohomology, when we have a exterior derivative. Also abstractly, if we have a delta set, abstract delta set, which is just a set of sets and a Dirac matrix. Dirac matrix encodes then the exterior derivative. So what we have is kind of very simple idea, but very, very powerful, is that we have this Dirac matrix produces a symmetry between even and odd forms. Right? If you have an odd form defined, function defined on simplices which are odd dimensional, then the image is in the even dimensions. So that allows us immediately, because D of course commutes with H, and so with the heat flow also what one has is that actually df is then just an eigen. If f is an eigenfunction, then df is an eigenfunction again, but in the other half, right? This is supersymmetry. Now that immediately implies that just by the Taylor expansion that works. Yeah, in matrices we don't have any elliptic regularity issues or anything, so no function analysis needed. This is just linear algebra. We can do a dynamic version of this by just composing this heat kernel with U. And so the same symmetry works also here. And what happens for t going to infinity, all the non-harmonic stuff goes away and you remain on the harmonic stuff, and the supertrace on the harmonic stuff is the Lefschetz number. This Lefschetz number is then equal to the supertrace which you have when t is equal to 0, which is just consists by definition just of the fixed points. And if you look what happens with u on the fixed points, then you get these indices. So that's how I did that just 13 years ago. So this can be extended probably much more, and but for now I'm actually just interested in also examples where we have continuous maps where this fails. I've not yet found an example where this actually fails, and where the attractor is not something more strange, not an open set and not a closed set. So that's it for today.